Criterion C. Investigating how changing the thickness of lead shielding affects the intensity of gamma radiation of radioactivity. So another student has decided to change the thickness of the lead shielding to see this affects, which affects the intensity of gamma radiation passing through it. In each trial of the experiment, they use a gamma source to measure the count rate behind different thicknesses of lead. So let us read what is it. Now you see this is a lead chamber they have put here. They put a gamma source over here. They put a Geiger-Müller counter. Geiger-Müller counter is nothing but a detector which is used to detect how many gamma photons are passing. Okay, the moment you put across a lead shielding, the more number of photons cannot pass. It actually stops or filters the gamma photons. Okay, calculate the percentage of gamma radiation that passes through a 1 centimeter thick lead shield. The initial count rate was 1000 counts per minute. Here it is 1000 counts. And the count rate after shielding was found to be 500 counts per minute. Which means what? If the shielding was not there, all the 1000 were passing through. If the shielding was there, only 500 was passing. Okay, and he is asking you to find out what is the percentage of gamma radiation. How do you find percentage? Take final minus initial, difference between these two, which should be 1000 minus 500 divided by the initial. Initial was 1000, so thus you have 500 divided by 1000, which is equal to half. Okay, so this is your relative value, and if you multiply this by 100, you get the percentage. So it is 50%. The 50% of the incoming radiation was seen to be shielded by the lead shield. Okay, now let me move on to the next. The student, okay, here we need to write this, okay, because you say calculate. Calculate has been given, so you need to write one line, because what's the mark here? 2 marks over here. Only so much is not sufficient. You need to write 50% of the incoming photon beam gamma radiation was shielded by the lead shield. That's what you have to mention. Next, the student used the same gamma source and the detector in every trial of the experiment. Outline how this helped to ensure the validity of the data. It means what? You use the same source and also the same detector, same Geiger-Müller counter. This one, and how did it actually ensure the validity? See, what happens in radioactivity is that radioactivity is a very highly chaotic phenomenon. Okay, so today if I'm able to observe something, okay, now next moment it might change. Okay, so there is no deterministic value of saying only the same thing. But so as a result of it, it's always better. Okay, so you need to outline. You need to say first one, what do you need to say? You need to mention about the source, and second you need to mention about the detector, and only then you get 2 marks. First one about the source. So radioactivity is always a chaotic phenomena, or you can say the number of gamma photons that decays from a sample per unit time will vary with time, and hence same source is recommended. This is the first one. Second one. Now let us look at the detector. The detector used here is your Geiger-Müller counter, GM counter. Certain GM counters are highly sensitive, certain GM counters are not so sensitive. Okay, GM counters are usually sensitive equipments whose counting rate depends on the efficiency. What do you mean by that? Let us say, for example, now as we have seen, there were around 1000 photons which came. Only 500 of them were being detected properly. Okay. But if you use a different instrument, there is a possibility, though 500 comes out of the lead chamber, only 450 can be detected. Okay. It all depends upon the efficiency of the instrument. So therefore, it is recommended. That same instrument is used forever. Okay. It should not change, because the moment you change, then the sensitivity will also change, and as a result of it, different instruments can record different values. So the next one. The student recorded the raw data in the notebook as seen. Organize the student's raw data into a table. See, this is the way how the raw data is recorded. It should not be like this. Right? So how it should be recorded? It should be like this. So yeah, we should say lead shielding in centimeter. So this should be the first column. After that, we should have trial 1, trial 2, trial 3. Let us put this, and then as mentioned, all this will be measured in what? It will be measured in counts per minute. Counts per minute, right? Now let me put columns. Now what you do? First you start with 0 centimeter. So 1, 0. Do not write the unit once again here. So I am not going to write trial 1, trial 2, trial 3 again. You are just going to write the values only. 1000, 1000, 1000 as such. 1 centimeter, 1.0. So here it is 510, 495, 409. Second one, 2 centimeter. Now here you see this 200, 210, 190, 220, 210, 190. Okay. The student has really made a mistake, you know. He has done it once and again he has written it something. Maybe while copy pasting he has made an error, or what is that, we are not sure about it. What we'll do is to understand or to write it appropriately, okay, we'll just go back to the next question here before coming back. Because in the next question I have observed, okay, so that for the lead thickness was 2 centimeter, given the raw counts for 2 centimeter thickness, 200, 210, 190. Now check for which one matters. 200, 210, 190, 200, 210, 190. This has been used, this has been discarded, right? So therefore, we will use this one once again. Yeah, we will use 200, 210, 190. Close it. That's it. Okay, we come to it. Finishing this particular part. Now let me move on to the next one. The student then constructs a process data table for each trial. They calculate the average count rate and the fraction of the radiation emitted. Okay. And then the background radiation was counted and measured as 20 counts per minute. Okay, using data from part C. So this is a background radiation. What do you mean by background radiation? That means when you remove the sample, but still you are able to observe there are some counts. Why do we get? Because you know, phosphorus is present. Our body itself has calcium, phosphorus. So they are all radioactivity and they actually huge amount of counts. And that's one thing. Maybe in cement you have phosphorus, you have gypsum there. Okay. In plants you have, the leaves will have phosphorus. Okay. So all of them will be emitting a little bit of it. Okay. And as a result of this, so definitely there will be some amount of background count. But the background count will not affect us because you know it's very, very less. So using data from part C, calculate the net average count rate and the fraction of radiation transmitted for the trial. The lead thickness was 2 cm. Given raw counts for 2 cm thickness. Trial 1 is 200, trial 2 is 210, and trial 3 is 190 counts per minute. This is what has been asked. Now, what do we do here? So, let us take the net average. Okay, because we need to find out what is the net this one. So, the average which I calculate from here, be, calculate this, should be 200 200 210 plus 190 is equal to so much divided by T will be equal to, this is equal to 200 over here. And what is that you are doing? We are going to find out, we are going to, now you have a background count equal to 20. We are going to subtract this, but that minus 20, which will be equal to 1. So this is your 180 count per minute. Now you need to find out what is the fraction of the radiation emitted. That's what is being asked, right? So for this, calculate the net average count rate. This is done now. Average count rate and fraction of the radiation emitted for the trial. So that is being asked. So now what we do is we will count something like net average raw count. So initially when there was no lead available, so you had the first one here. See, we had 1000, 1000, 1000. So net average here is equal to 1000 counts per minute, right? And therefore, now the fraction that you need to calculate here, fraction is equal to, so 180 divided by, should I put 1000? Should I put 1000 here? I should not use 7 because there's a background count even here also. So I will minus 20 over here, which will be 980, right? So therefore, I'm going to put this here as 180 divided by 980, should now be equal to, let's calculate, what is this value? 180 divided by 980. Divided by 0, I get 0.1831836, 0.184, approximately 0.1. Okay, so this means only 18.4% of the actual source made it through that 2 centimeter lead. Write it out. 1.4% of the incoming radiation made through 2 centimeter lead block is present. Okay, so this, we have come to an end to this. I hope you understood this question. Many students were not able to answer this particular question because they did not understand what has been asked. So it's basically whatever you have done here, where you did this for 50%, right? Okay, you did 50% over here. The same thing we have done. The only difference is that, so here we calculated something like based on the data here, and there the data we have to do it for the 2 centimeter slab. Okay, and we have to reduce or we have to subtract the background count. Here we did not subtract the background count, there we subtracted the background count, and we found out this. Okay. So thus we have come to the end to this. So let us see criterion D for tomorrow. Thank you.